We'll now talk about the molecular orbitals for hydrogen. So first, let's consider two hydrogen atoms that are separated by a distance. So we've got HA and HB that are fairly far apart from one another. If we think about what the orbitals look like for this system, we could have two different options. One of them, they could both have the same sign, and the other one, they could have different signs represented here by the blue and the red. Now, we can actually write equations for the molecular orbitals for both of these situations. So in one case, we've got one SA and one SB having the same sign, so we'll have a plus here. Over here, they've got the opposite sign, so we'll have, say, one SA minus one SB. Now, in the case where they both have the same sign, this is our bonding orbital, or bonding sigma orbital. When they don't have the same sign, this is our anti-bonding orbital. So it's our sigma star orbital. Now this n that I've got drawn in here, this is a normalization factor, so that the total probability of finding an electron can potentially be equal to 1. We won't talk about that right now. So anyhow, we do have these two different characters, the bonding character, the anti-bonding character. Now, as these two atoms start to approach, their atomic orbitals start to overlap. And in the case of the blue plus blue, we end up seeing a constructive overlap. So we'll end up seeing a probability build up in the middle of the orbital in between those two hydrogen atoms. On the other hand, when we have one SA and one SB, and we've got the minus sign, as they start to get closer and closer to one another, we end up having a destructive overlap. And in fact, there's a node in this orbital where there's no electron density. There's no probability of finding that electron in between the left and the right. And again, we'll call that a node. Now we can draw something called a molecular orbital diagram. So here we'll have our energy scale. We can show the separated hydrogen atoms on the left and right of our molecular orbital diagram, and in the middle we have our molecule. So we have our atomic orbitals here, and these two have the same energy because if we had separated hydrogen atoms, those 1s orbitals just have the energy of the 1s orbital. And then we have our H2 molecular orbitals. Now, as the two atoms are approaching one another and this bonding molecular orbital is forming, it turns out that the energy of the bonding molecular orbital is going to go lower in energy. We call that corresponds to a stabilization of the energy. Whereas the anti-bonding orbital goes higher and higher in energy. It's destabilized. And so we end up seeing that we'll have two different energy levels, a lower energy level and a higher energy level. Now, when we start to fill in the electrons, we have some principles that we're used to with atoms that we also have for molecules. So we take our 1 electrons from each hydrogen atom, we have 2 total electrons, and we put them in. And in this case, we'll put them both into the sigma orbital that arises from the 1s orbitals. Put them both in here. We're going to use the Aufbau principle. So we start from the bottom and we build up. We have the Pauli principle as well, so we put in 1 upspin and 1 downspin electron for this particular level. If we had additional electrons, we'd start filling in higher electrons. But for hydrogen, that's all we have. Moving on, we can talk about what happens if we have p orbitals in a molecule. So we can also form sigma orbitals from p orbitals. In that case, they need to interact end to end. So if you have one hydrogen or nitrogen oxygen atom here with a p orbital. So this is our internuclear axis, so that these are interacting end to end. Again, we can have our p orbitals interact in either a bonding fashion or an anti-bonding fashion. As these things are drawn here, the anti-bonding is actually a little easier to understand. So if we have the anti-bonding here plus the anti-bonding there, we end up getting a molecular orbital that looks very much like the original p orbital and the other p orbital. And again, a node in between the two. Bit of a destructive interaction as this lobe comes close to that lobe. Now, so this anti-bonding, I haven't really had to change the direction. This is actually the plus direction. You've got the same orientation of both p's. For the bonding interaction, we'd actually have to take this second p orbital flip it around so that we have orange on this side and teal on this other side. Once the orange is over here, that orange can interact in a bonding fashion to form this type of molecular orbital, where again we have a bonding interaction between the two nuclei, which are located there and there. And then we've got the teal on both ends. So because we've had to flip this one around in order to get that bonding interaction, we have a minus sign when we write our orbital. So we can say that our sigma orbital is proportional to the 2pz from the A minus the 2pz from the B. Whereas the anti-bonding orbital, we have an equation that looks like 2pza plus 2pzb. Now this is for p orbitals that are interacting end to end along that internuclear axis, but we could also have a case in which the p orbitals are not aligned along that intermolecular axis, so they're perpendicular to it. And in that case, they can form pi orbitals. And so we could have pi orbitals in the x direction that are coming from p orbitals in the x direction, and also p orbitals coming out at us. That would be in the y direction in this case. I see I left a z here. It should be an x or a y instead of a z. Basically, if we took a px and another px, now the orange is on the same side, the teal's on the same side, and we get these pi molecular orbitals that have this bonding interaction in the middle. So we have a plus sign, everything's the same as they originally were. Again, this can happen in the x direction or it can happen in the y direction. Again, you get that bonding orbital. An anti-bonding orbital, on the other hand, can be formed if you have a p orbital. You take this other p orbital and you flip it over so that you have teal and orange, and then you get this orbital that's a pi star orbital. Again, we can have that in the x direction or in the y direction. That should be an x and that should be a y. We want to take a look at these molecular orbital diagrams for molecules. So, for example, we could have nitrogen or oxygen. Now, because the interaction's a bit stronger when we have this p orbital interaction along the axis than it is the p orbital interaction when they're perpendicular, parallel to one another, but perpendicular to the internuclear axis. So this interaction is not as strong as the end-to-end interaction. Because the end-to-end interaction is stronger, we typically see more splitting between that sigma and sigma star. There's less splitting between the pi's. It's a little more clear down here in this diagram. The pi's have not changed in energy very much compared to the p orbitals, whereas the sigma orbitals have changed a lot more in energy compared to the p orbitals. One difference between the nitrogen molecular orbital and the oxygen is exactly what is the relative energy ordering of the sigma and the pi orbital. So here we have sigma a little bit higher in energy than the pi. But in both cases, we're going to want to fill up those sigma or pi orbitals first before filling up any of the anti-bonding orbitals. So for nitrogen, there's some 1s orbitals that aren't shown. 2s electrons fill up the sigma and sigma star arising from the 2s. We have 3 electrons in each of the p orbitals for each of the nitrogens. And so then we have 6 total electrons that go in and fill up the pi and the sigma, but it leaves these completely unfilled. We end up with a bond order of 3, because we've got these 3 more bonding orbitals filled than we have anti-bonding orbitals filled. For oxygen, we have the 2s here, the 2s there. Again, that fills up a set of sigma and sigma star orbitals. We really think a lot about the p's. So now, instead of having just 3 per atom, we have 4 per atom, which means we now have a total of 8. So we'll put in 1, 2, 3, 4, 5, 6. We've got 2 additional electrons. Those go into the pi stars. Now we've got Hund's rule, which says when you've got 2 orbitals that it's the same energy, you put 1 in each one first before you pair them up. So with oxygen, it turns out you have 2 unpaired electrons. It's a triplet state. It also happens to be a magnetic molecule then. It would be attracted to a magnet if you poured liquid oxygen through a magnet. Yeah, so these orbitals then are used to form these molecular orbital diagrams.